Greetings everyone. So in this video we are going to discuss about our new topic, which is phenols. As we have discussed in our previous video that the alcohols, phenols and ethers are all belonged to the same family, which is the family of water molecule. It is resembling with the water molecule, which is having two hydrogen atoms attached to oxygen. But in case of phenol, the thing is pretty different. Instead of one hydrogen atom is replaced by a benzene ring, and that basically forms the structure of phenol. That phenol was discovered by Runge. Runge was the name of the scientist, and if you just look into some basic, very basic things, we have some common names. We have few important common names which come along the way when we discuss phenols. Whenever we are going to have a phenol, so basically, the way we are having monohydric, dihydric, trihydric alcohols, in the same way we are having monohydric, dihydric, and trihydric phenol. If there is one OH group, then it's a monohydric phenol. If there are two OH group, then it's a dihydric phenol. And likewise, trihydric phenol having three OH group. So, example of monohydric phenol is the benzenol. Benzenol, and we also commonly call this as a carbolic acid. Carb is the term used for the benzene ring, and oleic is the term used for the negative charge, which is given by the alcohol hydroxyl group. And if you were to discuss some of its important properties, it was uh, first discovered during the destructive distillation of coal tar. This is an important point to remember. And if you just talk about its characteristics, you know this is carbolic acid, benzenol, or the simplest structure phenol. Now, whenever we are going to discuss dihydric alcohols can be have three major examples, such that whenever we are going to have the alcohol group on the second carbon on the ortho position, orthophenol, then orthohydroxyphenol, then it's going to be named as catechol. It has a huge significance in the biological systems, as we have studied in biology as well. And if it is present on the meta group, on the meta position, then it is a resorcinol. And if it is present at the para position, then it is named as hydroquinone. So when the OH group is present on ortho, it is catechol; at meta, it is resorcinol; and at para, it is hydroquinone. Now, when it comes to trihydric phenol, trihydric phenols have one very famous example, which is known as the pyrogallol. So pyrogallol has three hydroxyl group. There's a first position, second position, third position. On the ortho and meta position, there is OH group attached. So this is known as pyrogallol. Now, let's just move on to the next part, which is some physical properties. If we just talk about the physical properties of phenol, it is having a boiling point which is 182 centigrade, while the melting point is 41 centigrade. And if we were to talk about its characteristics, it is a sparingly soluble salt. It is a sparingly soluble salt, sparingly soluble solid. It is colorless. It is colorless. Some books write that it is a white color in the pure form. In the pure form, it is whitish in color. Pure phenol is whitish in color with some reddish impurities due to the presence of oxides in it. Reddish impurities, which is basically due to the presence of oxides in it. Uh, Minor. So, colorless, it is crystalline, and it is delicescent solid, which is sparingly soluble in water. It forms a pink solution. It forms a pink solution in water that is sparingly soluble. and that solution has an upper consolute temperature or the critical solution temperature as 68.5 centigrade, which means that above 68.5 centigrade the phenol is completely soluble in water. This is on its upper consolute temperature or critical solution temperature, and it has a characteristic odor. Characteristic odor. It is a characteristic odor because of the presence of the aromatic ring, and on the other hand side, it is a poisonous compound. It is a very poisonous compound. Why do we call it as a poisonous compound? Of the presence of because the presence of the benzene ring at first, and for the second reason is that the benzene ring makes it pretty poisonous. So because of this toxicity, it is also used as a disinfectant. In fact, phenol was the first disinfectant to be used. First disinfectant or the first antiseptic to be used was phenol. It was in the early 1800s. So this is an important point to be considered. Now, when it comes to the structure, we would find a few similarities with alcohol and water. Again, if you talk about oxygen, it is having sp3 hybridized orbital, but at that point, sp3 hybridized orbital of oxygen is attached. Sp3 hybridized orbital of oxygen. This time, it is attached sp3 sp3. This time, this orbital is attached to the carbon of the benzene ring. It is a carbon of the benzene ring, right? And that carbon of benzene ring is attached to the oxygen, which is sp2 hybridized. This carbon of the benzene ring is sp2 hybridized, which is attached to sp3 hybridized orbital of oxygen, and that basically forms this overlap. Now, on the other hand side, let's draw the other structure as well. Let's draw the other structure. Here we have the oxygen. We have the s orbital. We have this s orbital. So let's draw the s orbital of hydrogen, and this is basically the structure. Now if you are supposed to look into the structure in detail, we will actually see one important thing over here, that there is again the formation of sigma bonds. All of them are sigma bonds, but the strength of oxygen to hydrogen bond is greater than carbon to oxygen bond, and this is due to this reason that this is due to this reason that nucleophilic reactions are more likely to happen as compared to nucleophilic reactions are more likely to happen than electrophilic reactions. So this is an important point. And when it comes to the bond angle, because there is a presence of benzene ring, there is not much of repulsion between benzene ring and hydrogen, due to which the bond angle is somewhat around 108.5, 108.5 or 9, 109, something around that. So this is the bond angle. And again, the structure, when it comes to the structure, it is a tetrahedral geometry, and it is a bent structure. There is a short distortion. Bent structure, there's a short distortion, which is because of the repulsions between the two lone pairs of oxygen. Alright, now let's just look into the acidity. Acidity of phenol is in such a manner that phenols are acidic in nature. Why? Why are they acidic in nature? Because the oxygen to hydrogen bond which is formed in phenol, there is one characteristic, that oxygen to hydrogen bond can be correlated with the carbon to oxygen bond. Carbon to oxygen bond is smaller in size. Smaller in size. And due to this reason, the carbon to oxygen bond cannot be easily, it is smaller in size, and due to this reason it forms a stable phenoxide ion. Phenoxide ion. Now, what is a phenoxide? Let's say if I take phenol, I take a phenol, right? I take a phenol. This is OH group attached, and I react it. I'm not reacting it. I'm dissolving it in water, right? In water, it is ionized. It is ionized. In water, it is ionized. So, in water, when it is ionized, it will form an ion, which is known as a basic ion, which is known as a phenoxide ion. Phenoxide ion. Now that phenoxide ion, which is formed, defines the basicity. It is a basic ion. Because of the presence of negative charge, it is a basic ion, and that phenoxide ion defines the acidity of phenol, alongside which we get hydronium ion. Now let's just look into phenoxide ion. Phenoxide ion basically is a conjugate base, and we have understood that whenever the conjugate base is going to be the stronger, then there would be less acidic characteristics. So basically, if we just look into the structure of phenol, phenol has something we call as resonance. It has resonance. What is meant by resonance? We have studied in benzene that when there's delocalization of pi electrons, it's going to create some multiple resonance structure. There are 5 resonance structures which were created in benzene. Likewise, the resonance happens in phenoxide ion as well. How does the resonance happens? It again happens when the electrons of the oxygen atom delocalize with the pi electrons of the benzene ring. When the electrons of the oxygen atom delocalize with pi electrons of the benzene ring, at that point they are going to produce resonance structures. Let me explain it through the diagram. It is the same reaction that I completed here. Over here, what actually happens is oxygen delocalizes its lone pair electrons to the benzene ring's pi electrons, due to which the pi cloud is then existing in the form of a resonance structure. As you may see, there are around 4 resonance structure, and actually there are around 4 to 5 resonance structure, which make it pretty stable ion, and because of resonance it is very stabilized, right? It is very stabilized. So we have understood when there is a stronger conjugate base, there is a weaker acid. So because of the stronger conjugate base, because of the stronger conjugate base, there should be a weaker acid, and this is the reason that phenol is having its dissociation constant as 1.3 to 10 power minus 10, or the pH value as 5 to 6, which means it is slightly acidic, right? And if you were to talk about, you know let's say if I were to draw a comparison series of acidity, such that I write acidity here, and I compare 4 things. I compare carboxylic acids. Let's say I take acetic acid, and I take phenol, and I take water, and I take alcohol, right? So I take these 4 things. So if I'm going to compare them, the acidity would be greatest in the carboxylic acid, and then it would be the phenol, which would be having the second most acidity, then water, which is having third most acidity, and then alcohol, which is the least acidic. The pKa value of acetic acid is 5. For phenol, it is 10. It is also same for thiol groups. We are going to discuss thiol groups at the end as well. And pKa for alcohols is somewhat around 16 to 20. So over here, why does this difference happens? Why does there such an acidity difference? Well, the reason behind it is that number one, it is the ability of phenol to make ability of phenol to donate its hydrogen more easily than alcohol. In alcohol, the oxygen in alcohol the oxygen is not having the oxygen to hydrogen bond is somewhat weaker. If I were to explain it in very simple terms, the oxygen to hydrogen bond in alcohol is weaker than the oxygen to hydrogen bond in phenol. And why does that bond becomes weaker? The reason behind it is delocalization. What actually happens is the phenol when it is dissolved in water or any acid, it forms phenoxide ions, and that those phenoxide ions ultimately those phenoxide ions basically perform delocalization, due to which they form resonance structures, due to which their stability is increased. And because of the increase in their stability, they are going to be they do see when the phenols are going to be stabilized. I take a phenoxide ion. I take a phenoxide ion. This is a phenoxide ion, right? This phenoxide ion here, it is having resonance in it, and because of the resonance happening in this phenoxide ion, I cannot say that it needs an electron. It needs any electron. It does not need any electron. It does not need a chemical bonding. So when it is going to have a proton with it, would the proton be able to form a bond with it? No, it won't be able to do so, because it is a stable structure, and because of that stability, it is unable to take this proton back into its structure and thus form a phenol molecule again. And due to this reason, this proton which is present over here remains within the solution. It remains within the solution and thus reacts with another compound, due to which its reactivity increases, and thus the acidity of the solution also increases. And it is due to this reason, because of the strength of the phenoxide ion, the acidity of phenol also increases. And this is an important point. Acidity of phenol due to this reason increases, and that acidity is greater than alcohols. Alcohols do not have delocalizations. They do not have delocalization phenomena, due to which the alkoxide ions that alcohols form. Alcohols form alkoxide ions, which are less stable than phenoxide ions, due to which the acidic hydrogen which is taken from the from the alcohol then are also very uh, difficult to give by the alcohol to form alkoxide ions, due to which the phenoxide ions can easily give away its proton, as a result of which the phenols are more acidic than alcohols, and thus from water as well. And but they are not that acidic than carboxylic acid. Reason behind it is that carboxylic acid, if you just look into the structure of carboxylic acid, it is having two oxygens. There are two oxygens which are giving the electrons to this carbon, right? There are two oxygens. There is one oxygen over here which is giving its electron to carbon, and another oxygen which is here, which has its electron density here. Because of two oxygens which are present, the electronegativity of this carbon, the electronegativity increases. This electronegativity of because of the high electronegativity of oxygen atoms, the bond strength increases, due to which this entire structure oops, this entire structure becomes pretty stable, due to which it is much easier for the due to which it is much easier to break this bond and give away the hydrogen. This is the reason, because two oxygen atoms, even though it is not having delocalization, but it is having two oxygen atoms, due to which it can easily give away its proton. All right. So the this is all about the phenols acidity. Now let's just move on to some reactions. One reaction which we are going to perform over here is the reaction of phenol with sodium. When phenol reacts with sodium, it forms sodium phenoxide and it evolves hydrogen gas. And when reacts with sodium hydroxide, it forms water and sodium phenoxide. And there's another reaction, a very famous reaction is there, which is known as Kolb Schmitter Kolb Schmitter reaction. Reaction which is known as Kolb Schmitter reaction. Now, what does this reaction include? This reaction basically includes a carbon dioxide molecule. There's a carbon dioxide molecule, and that carbon dioxide molecule reacts with a phenol. A phenol, right? When it reacts with a phenol, what actually it gets is at the first point, at the first point, this carbox. Now, if you just look into oxygen, oxygen is partially electronegative. It's partially electronegative, and that makes the central carbon electrophilic, partially electropositive, due to which it becomes an electrophile. That electrophilic carbon tends to attack. It tends to this this carbon tends to come and attack over here. It will come and attack over here. It will come and attack here, attack over here, come and attack in this place. So when it will attack the phenol, what it will actually make is what it will actually make is it will make actually we are going to have one more thing over here. We don't only have carbon dioxide, but we also have sodium um, hydroxide over here, right? We have sodium hydroxide here as well. So in this way, we will basically what actually happens is that this reaction takes place in two steps. In the first step, there is formation of the sodium. In the first step, there is a formation of sodium phenoxide. Sodium phenoxide. When the sodium hydroxide reacts with the phenol, it produces sodium phenoxide and water. And that sodium phenoxide, when it further reacts with carbon dioxide, it produces what I call as sodium hydroxybenzoate. Sodium hydroxybenzoate. Just try to draw the structure. Sodium hydroxy. Oops, it is going to be this part. It is going to be on the second part. So it is OH attached. So sodium hydroxy benzoate. So this is about it. This method is known as Kolb-Schmitter reaction, and this is basically a carboxylation reaction in which there is carboxylation happening of the phenol group. Alright, now let's just move on to another part, which is the preparation. How do we prepare phenols? Phenols can be prepared by react in two major ways. Number one method is through sodium benzene sulfonate. When we are going to react phenol, when we are going to react sodium benzene sulfonate, sodium salt of benzene sulfonic acid with sodium hydroxide at 360 temperature, 320 centigrade. It's not 360 centigrade, it is 320 centigrade. When you're going to react it at 320 centigrade, then at that point what we will actually get is we'll actually get sodium phenoxide and sodium sulfate. It is the byproduct which would be removed, and then sodium phenoxide would further be treated with HCl or H2SO4, due to which we will get phenol. Second reaction is known as the Dawes process. It is the Dawes process. It is in this we use the reagent which is chlorobenzene. We take chlorobenzene and we use sodium hydroxide at 360 centigrade at 150 atm, due to which we get sodium phenoxide ion first, and then we further treat it with HCl, due to which we get phenol. Second is diazonium salt. We have previously studied that when we are going to react aniline with HCl at a very low temperature below 10 centigrade, when we going to react it below 10 centigrade, uh, below 10 centigrade, at that point we are going to get a diazonium salt. Whenever we are going to react, then that diazonium salt, the type of diazonium salt which we are going to use is benzene diazonium chloride. Benzene diazonium chloride. So I use benzene diazonium chloride, and I what actually do is below 10 centigrade. I what I actually do is I take benzene diazonium chloride and I perform its hydrolysis, due to which it will give me phenol and nitrogen and HCl. Now there are three ways. I can either use water, or I can use heat, or I can use dilute HCl, dilute acid. This is the entire thing. This is how we can actually prepare it. Right. And when it comes to some of its reactions, um, if you were to look at its reaction, it is broadly classified into two major categories. Number one category is the reaction which happens due to the oxygen to hydrogen bond, such that when the oxygen to hydrogen bond is broken, then at that point it causes a reaction, which is mostly known as electrophilic reaction. And second reaction, which is this reaction is an addition reaction, right? And second type of reaction, which is due to the benzene ring, that reaction is a that reaction is basically a substitution reaction. That type of reaction is a substitution reaction, because benzene ring is itself nucleophile. Benzene ring is itself nucleophile, right? And that nucleophile is attached. Sorry, this is a nucleophilic substitution reaction. Benzene is a nucleophile, but again, the nucleophile which attaches with benzene is replaced by another nucleophile. So this is nucleophilic substitution reaction. These are the two reactions. Nucleophilic substitution reaction is pretty common. We have already studied the mechanisms as well. What we actually do is we take phenol, and whenever we are going to react it with dilute nitric acid, then we are going to get orthonitrophenol and paranitrophenol. This reaction is carried out at room temperature, 25 centigrade. When you're going to react phenol with concentrated H2SO4, sorry, concentrated HNO3 nitric acid, and we provided, carry that reaction at 25 centigrade or room temperature, we will get trianitrophenol, also known as picric acid. This picric acid is very explosive. It is used in, creating bombs and explosions, and for that purpose, because of this reason, we whenever we are going to store picric acid, we first create a layer of water in the bottle, and then we put the picric acid in it so that there is no blast. And then we have sulfonation reaction. For sulfonation, we use a sulfonating agent, which is H2SO4, concentrated H2SO4 at 50. Now that concentrated H2SO4, when it is reacted with phenol, it will produce benzene sulfonic acid. If this reaction is carried out at 15 to 20 centigrade at a low temperature, it is going to produce ortho benzene sulfonic acid. At a high temperature, it is going to produce para benzene sulfonic acid, para hydroxyl benzene sulfonic acid. And there's another reaction which is known as bromination. When bromination is carried out in an aqueous solution, then it's going to produce tribromophenol. But if bromination is going to be done in an inert solvent like carbon tetrachloride, then it's going to produce orthobromophenol and parabromophenol. Now there is another reaction, very important reaction, which is the reaction of phenol with sodium phenoxide. Basically, whenever phenol is going to react with sodium, it's going to evolve hydrogen gas and produce sodium phenoxide. This hydrogen gas serves as a brisk effervescence. We call this as brisk effervescence, which basically tells us brisk effervescence. This reaction is the identification test for the presence of phenol or alcohol. Such that whenever there is presence of phenol or alcohol, when we react sodium or with phenol or alcohol, we are going to get hydrogen gas evolved, which indicates there is either the presence of phenol or alcohol in solution. Due to which it is an identification test in which the brisk effervescence, which is a hydrogen gas evolved, brisk effervescence give us the indication. Now, when we are going to take phenol and perform its oxidation, usually phenol does not undergo oxidation, but when we are going to provide use a very strong oxidizing agent like potassium dichromate in the presence of sulfuric acid as a catalyst, then at that point we are going to get a benzoquinone conjugated diketone, which is yellowish in color. And that benzoquinone uh, has a lot of applications in medicine, because it is used for the preparation of antibiotics, for pharmaceuticals, used as a staining agent. It is used as a staining agent in biological specimens, and it is also used as a photograph dissolving agent, photograph um, photograph photograph detaching agent, and these are some importance. Now, when it comes to another reaction, which is the reaction of alcohol, reaction of phenol with sodium hydroxide, due to which it produces sodium phenoxide ions again. Now, when sodium phenoxide ion reacts with carbon dioxide, this is again the same reaction which we studied previously. That was the reaction on, no, this is actually the same reaction which we studied previously. It is the Kolb Schmitter reaction. What actually happens in Kolb-Schmitter reaction is the sodium phenoxide ion which is produced that reacts with carbon dioxide, due to which it produces sodium hydroxyl benzoate, hydroxyl sodium benzoate. If it is carried out at 15 centigrade at a very low temperature, then it's going to produce ortho sodium hydroxyl benzoate. But if it is going to be at high temperature, then it will produce para sodium hydroxyl benzoate. This is an important point. Now, these are some of the reactions which we have done. If we were to summarize it all, we are going to get this. For nitration, we use nitric acid. For nitration, we use nitric acid. For sulfonation, we use sulfuric acid. For halogenation, we use halogen molecules. For alkylation, we use alkyl halide, or in the presence of Lewis acid, or alcohols. And for acylation we use the acyl group, uh, acyl acyl halide. And for nitrosation, again nitrosation was an important reaction that I believe should be discussed over here as well. Basically, whenever we are going to react, I take a phenol and with I'm going to react it with oops I'm either going to react it with sodium nitrogen dioxide, or I take nitrous acid. I take one of these sources. At that point, what actually happens is I will get this. I will get a nitrosophenol, a para-nitrosophenol. This para-nitrosophenol is of particular importance because this forms a tautomeric structure. This forms a tautomeric structure such that what actually happens in its tautomeric structure is that this hydrogen, which is a mobile hydrogen, will go at this part, and it will what it will actually do is, let me just draw its tautomeric structure. The tautomeric structure would be like this. This this would form an oxygen bond here, Oxygen will form a double bond. Here, nitrogen, which is going to attach with OH, and then the double bond, which was, let me just draw it pretty clearly so that it becomes easy to understand. Okay, so see, this is the hydrogen which goes here, right? And this is a double bond actually. So this double bond goes here, right? And a double bond comes here, right? Due to which this is the actual structure formed. Let me just draw it more clearly. Here we have the double bond. Here, this is an isomer. And what do we name this isomer? This isomer is named as para para nitrobenzene monooxime. This is basically an monooxime, an oxime isomer, and an oxime tautomer, oxime group, which is an unstable group. So for this, we either use nitrous acid. In our books, it is mostly written nitrous acid, but we can also use sodium nitrous. All right. So that's all about it. Now let's just move on to some basic things. We are going to understand the very basic difference between alcohol and phenol. Again, it's a summary of all what we have discussed for the past few days. When it comes to functional group, both are having functional group hydroxyl group, but in alcohol it is attached to alkyl carbon, but in phenol it is attached to aryl carbon. Hydrogen bonding, both have the capability to form hydrogen bond, but phenol forms a stronger hydrogen bonding as compared to alcohol increased because of the increased acidity. Boiling point is generally lower in alcohols, and it is greater in phenols. Acidity is greater in phenol and lower in alcohol, and solubility is greater in alcohol and lower in phenol. Aromatic properties are present in phenol but not in alcohol. These are some points to be understood. Alright, now let's just move on to some important tests for the identification of alcohols and phenols. For identification of alcohols, we basically react sodium with alcohol, due to which we get when there's evolution of hydrogen gas, and that serves as a brisk effervescence. That brisk effervescence is basically indicating that there is hydrogen gas being evolved, and due to this reason, we basically know that there is some hydroxyl group present. Either it is in a phenol group or in an alcohol group. So this is how we use this test for phenol as well as alcohol group identification. Second test is esterification. What I actually do is I take alcohol and I react alcohol with acetic acid in the presence of a concentrated H2SO4 catalyst. I will get ethyl acetate. So whenever I'm going to produce ethyl acetate, it will give me a fruity smell. A fruity smell of ethyl acetate ester would be formed. And whenever I'm going to get that fruity smell, it means that there is ethyl acetate ester formed, and that ultimately means that the product which I react, the reagent which I used for my reaction was an alcohol, due to which it is an identification test as well. Then we have some identification tests for phenol. Number one test is the reaction of phenol with a freshly made ferric chloride, also known as ferric chloride test. When freshly made ferric chloride reacts with phenol, it's going to produce an ion complex. Basically, it is a ferric phenoxide complex. A ferric phenoxide complex. The formula is like this. We've got formula is like this. We've got you know the H3, and there is iron, and this is C6H5, and let me just draw here. Yes, this is it. Sorry, one more important thing. There is all right. So this is the complex form, and this complex is basically known as ferric phenoxide complex, which is a violet, purple, or bluish in color. Whenever we are going to form ferric phenoxide complex, we will get a violet, purple, or bluish color, which indicates that there is the presence of phenol. When phenol is going to give, this is a bromine water test. Whenever we are going to react phenol with water, when you're going to react phenol with an aqueous bromine, basically bromine water is brownish in color. It is a brownish water. It is brownish in color, reddish brownish in color. When you're going to react it with phenol, it's going to produce tribromophenol, which is a white precipitate. It is a white precipitate of salts, white precipitate of salts. So these bromine water, which is reddish brown in color, when the reaction completes, the reddish brown color starts to discharge. It becomes colorless, and there is the dischargeal of some white precipitate of tribromophenol, which indicates that there is presence of phenol. So this is how we can identify. Now when it comes to some importance of phenol, number one importance is it is used as a disinfectant. It is used as a disinfectant and antiseptic. It was one of the first disinfectant and antiseptic used because of the toxic properties. And number two is that phenol can be used. Phenol can be used for acidic, for the production of various important compounds such as esters, for production of aryl ethers. Aryl ethers, basically these are this is again a class of organic compounds. It's like this: C6H5OR. This is aryl ether, and they can also be used for production of phenolphthalein. And again, they can be used for the production of polymers. They can be used for the production of polymers. Polymers such as bakelite can be formed with the help of phenols. So these are some of the uses. Now when it comes to thiol versus alcohol, now we have completed phenols, and now it is important to understand an analog of alcohol, which is known as thiol group. This is a thiol group. Again, the structure of thiol is as it is similar to the structure of thiol is as it is similar to alcohol. There are few differences which we are only going to discuss here in terms of reactivity, in terms of chemical properties, and in terms of electronegativity and other stuff. So when it comes to the physical properties, how are we going to name it? Let's say if it is methanol. If I want to write a thiol group which is having one carbon, then I'm going to write it as thiomethanol, right? And in that way, I'm going to add this prefix theo to the alcohol number of carbons, and then it's going to become the name for that particular thiol group. Now, when it comes to the first and foremost part, thiol group, it is having less hydrogen bonding than alcohols. It is having less hydrogen bonding than alcohol. It is having less boiling point and melting point than alcohol. And why is that so? That is because of the large size of sulfur, because sulfur is actually large in size, due to which it has less nuclear attraction, due to which it forms less stable bonds, due to which um, because of the less stable bonds formed, it is more reactive. It is more reactive and forms, and because of the more reactivity, the sulfur to hydrogen bond which is formed in the thiol group is weaker is weaker. And Due to this reason, it is acidic, more acidic. Yes. And then we have the electronegativity. Electronegativity of sulfur is less than oxygen. Oxygen is more electronegative than sulfur. And due to this reason, oxygen being more electronegative than sulfur, sulfur forms weaker hydrogen bondings than alcohol and boiling point than alcohol. So this is an important consideration. Now if we just talk about sulfur, again it forms sp3 hybridized orbitals. There are sp3 hybridized orbitals formed in the thiol group, uh, but the sp3 hybridized orbitals formed are weaker. The bonds are actually weaker as compared to oxygen because of the large size of sulfur, right? And another important thing which needs to be considered over here is that thiol group is a stronger nucleophile. Thiol is a stronger nucleophile. When thiol is just the way we are having alcohol forming alkoxide ions, right? This is alkoxide ions. The sulfoxide ions which are going to be formed, sulfoxide ions which are going to be formed by removing proton from deprotonation of thiol, that would be more stable than alkoxide ions, due to which thiol forms a stronger nucleophile. And there is another important thing that I would like to discuss, which is the oxidation. When thiol is going to be oxidized, when thiol is going to oxidize, it is going when thiol will oxidize, it will be oxidized into when thiol is going to oxidize, it is going to oxidize into sulfur to oxygen system, into sulfur and oxygen, rather than rather than sulfur to oxygen system, rather than sulfur to carbon system, because carbon to sulfur system and oxygen to sulfur system both are the possibilities of the products of oxidation of thiol group, but the more likely product is sulfur to oxygen. Sulfur to carbon is less likely to be present, because sulfur to oxygen, again, it's a strong bond, and that's going to be more beneficial because it's going to be more stable. All right. And the most common oxidation product is a disulfide. Most common oxidation product in sulfur, in thiol groups, whenever we're going to perform oxidation of thiol groups, we will get this product, which is known as dialkyl disulfide. Disulfide. Dialkyl disulfide. And this is an important reaction. This is a biologically important reaction. Biologically important reaction. Why is it biologically important reaction? Why is it biologically important reaction? We have heard that there are certain amino acids. There are certain amino acids, certain proteins which we call as tertiary proteins. Those tertiary proteins, we are going to study the structures of proteins in the upcoming chapters. But tertiary proteins, for now, they have a special kind of physical force, which is known as a disulfide bridge. A disulfide bond, also known as a disulfide bridge. That disulfide bond or disulfide bridge is this. This is a disulfide bond. This is a disulfide bridge, which is formed by the oxidation of the thiol group in the amino acids. So that is responsible for the stability of protein. And this is again an important thing, an interesting thing as well. So that's all about this video. Hopefully you enjoyed it, and hopefully we'll meet again in another.